Okay, we have two new announcements. So we have the old announcements, which are that homework 1 is due tonight, and other announcement, which is that lab sections are still happening this week. In fact, they'll happen next week as well, and I'm going to just remove that from future announcements. Then the new ones are that the programming assignment is out, and it's due September 27th. Now, I know September 27th is like years away. You don't have to worry about it at all. But let me just suggest that you take a look at the programming assignment just really quickly. Don't commit to it, just like look at it. Just to sort of understand what it's asking about without committing to actually working on it, just so you get it in your head. You know what's what. And then finally, I have figured out how to get the lectures onto YouTube. It turns out it's not rocket science. It's actually pretty easy. It's just that I was pretty confused, but this should all be there now. Today's plan. Oh, any questions about the announcements? Today's plan is to talk about insertion sort, talk a little bit more about loop invariance, and then talk about the memory model on a computer so that we can understand pointers and things like that, and linked lists and other such linked structures. That's the plan. Is it good? Any questions? No. Okay. Here's actually selection sort, not insertion sort. Selection sort was what we did last time. We had find min that we proved was that's the one that finds the smallest element in an array starting at location I and looking towards the larger indices in the array. So I guess larger is this way. So that was find min. It found the smallest thing in the array, and it from position I onward. And what selection sort did was it took the result of find min and it swapped the array location I with the array location min in order to put things in order for that particular iteration, for the ith iteration. Okay? So of course we came up with this loop invariant that said, great, we're making progress by sorting the first I elements of the array A. Not only are they sorted, they're the smallest elements in the array A. And in addition, we haven't changed any of the strings in the array A. So that was the loop invariant. Do you remember this? Did we do this? Did we talk about this? Yeah? No. Yes? Yeah? Okay. Okay, good. Because everybody's sort of just looking like... And I have to tell you, all day today is not going to be about loop invariance, so don't worry. It's not going to be that. But I'm not going to go over this slide at all, except for two things. There are two things on this slide. One is to consider the base case. So we would like to show that this statement about the sortedness of the array A is true when the index I is 0. Before the 0th iteration of the loop starts, we'd like to say it's true. And the trouble is that if I look at what the loop invariant says at that point, it says that the contents of A0 through 0 minus 1, which is minus 1, are the I smallest strings in A, and they're in order. So I'm just pointing this out as being somewhat interesting, that we have a range 0 to minus 1, which in this means empty. If it was 0 to 0, then it would be one element, the 0th element. If it's 0 to minus 1, or minus 2, or minus 5, it's empty. There's nothing in there. And so the question is the base case really true? It's supposed to be the case that the contents of this array, A0 through minus 1, which is nothing, are the zero smallest strings. Then it's empty, so there's no strings in order. Well, there aren't any strings, so not only are there not any strings, but there's not any strings, and they're also in order because there aren't any of them. So this is basically what's sometimes called a vacuous statement, because there is nothing to talk about. But I just wanted to point that out because it can be confusing. Is anybody still confused? No. It worked. Done. The second thing I want to talk about on this slide is this question. Why? So that's sort of sad because that means we have to read the whole thing. But let's just read it really quickly. So we know what it's going to say. It's going to say there is an inductive step, which is basically we're assuming that the statement is true at iteration I. And by the way, I has to be less than n because if it was equal to n, then we wouldn't actually iterate, we wouldn't actually enter the loop. So we only need to prove the inductive step when I is less than n. Okay? So that's why this less than n is there. Only need to prove the inductive step for I up to n minus 1. Let me just put in there for I equals 1. For I equals 1 up to n minus 1. It doesn't have to be proved for n because we don't need to take a step when we're at n. It's the end. Okay, so anyway, we know what it's going to say. It says, first of all, we got this inductive hypothesis. Then we've got this inductive step that we have to prove. But we know exactly what that's going to say because we know that we're going to invoke findmin, and findmin will return the index of the smallest string in ai through n minus 1. It will return the index of that smallest string. And then we will swap ai with a min. And that immediately tells us, because of the correctness of the find operation, that that is true. AI is now, we know, less than or equal to all of the other strings that are in the array from I plus 1 to n minus 1, because of the swap and because of the correctness of findmin. Okay? I'm asking why about this. About the last inequality. Why is it true that AI is greater than or equal to A0 through AI minus 1? This is required because we want to prove that the array is sorted and also that it's the first I location, or I plus 1 locations are the smallest. We need to show that AI is in the right sorted order. And so it has to be the biggest of all of the elements that are A0 through AI minus 1. It has to be greater than or equal to 1. Why? This is not a trick question. It's just a question.
When you swap it, the smallest one goes to the left side. So this one goes to the right.
Yeah, that's this right here, right? The swap is saying that AI, which was the smallest in the array AI through n minus 1, that was called a min. A min was swapped into the location AI, and therefore we know that AI is smaller than everything that's here. So you're absolutely right. That's what findmin did, though. And I'm asking about this. Where in the world did this come from? That's not from correctness of findmin.
Well, if findmin is putting like the smallest letters at the beginning, then where you stop should be greater than everything before it.
Is findmin doing that? What are you relying on to prove that that's true? I mean, certainly you're relying on findmin essentially, but there's something immediate in this proof that you can use to say this is true. And you would replace this y with this little phrase. Yeah.
Isn't that just the inductive hypothesis?
Exactly. It's the inductive hypothesis. This is saying that the original array locations A0 through AI minus 1 are smaller than all of the array locations, all the contents of the array locations AI through n minus 1. That's what it says here. The contents of A0 through AI minus 1 are the I smallest strings in A. And that means that this guy, who isn't one of those, must be bigger, or at least as big. So this is the inductive hypothesis. So you would write by the inductive hypothesis. And that's why we needed a strong inductive. We needed more than just that A0 through AI minus 1 was sorted. We needed that it was sorted and small. We needed both. Any questions about this? All right, great. So we're done with selection sort. Now we have another mystery function. Another mystery function. Looks just like the other mystery function. It's assuming that A0 through A minus 1 is sorted. It's taking in some index I. It's pulling a value out of A at A sub I. But now it's doing something different from the last mystery function that we looked at. Remember, the last one was the one that was eventually named findmin. It was using selection sort. This is slightly different because it starts with an index j, and j starts at I, and it decrements j. So j is going to be looking at the array locations that are before array location I, or at or before array location I. It's not even going to go down to this part. Findmin looked at everything that was after I and afterwards. This is looking at stuff before. So let's think about what this does. And one way to think about what this code does, and I encourage you to do this when you want to understand code, even when you're sitting in a final exam and you don't feel like you have time to write anything down, this is a good idea to do if you need to understand code. And that's to write something down, which is, in our case, a little example. We have down here at the bottom an example input array A with these values, an example input I, which is 3. And the first thing that this code does is it sets value to be the location, or the value in location 3 of array A. So value is 15. And then it enters the loop with j equal I, which is 3. And what does it do? Well, it checks that j is 0. It's not. It's big. And then it says, is a j minus 1, so is this guy, is it bigger or smaller than val? And if it's bigger than val, which it is, 30 is bigger than 15, right? This is 15, this is val. 30 is bigger than 15, then what does it do? It like copies. It copies a j minus 1 into a j. So it's moving this here. Oops. All right, nothing's working. That's okay. It's good that I didn't have to restart the computer. That's my last resort. So it copies the A2 into A3, and then it decrements j, and it tries again. It says, now if I look at j minus 1, which is this guy, is it bigger or smaller than val? It's bigger, and so it copies it. And we're going to do it again into that location. Look at this array. It's got duplicates, 10, 20, 20, 30. Crazy. But the next step sort of figures out what happens. In this case, when j gets down to 1, then it checks against the array location A0, this one, and it says, no, that one is smaller than 15, and so it falls out without doing any copying. And at the bottom, after it falls out of the loop right here, it copies value back into the array at location j. So that's where this 15 comes from, as it gets copied in. Okay? This is what the code does, and now, is it clear? It's, how many people play Bridge, the card game? How many people have played Bridge? Ever? Wow. This is the first class that I've ever had that nobody's played Bridge. Wow. I'm old. Anyway, it used to be a card game that people used to play when they had to socialize somehow and they didn't have the internet. So there's a card game, and it involves sorting your hand, because you have to sort the cards by order or else you won't know whether your hand is good or not. And you've got 13 cards. That's a lot of cards. So what you do is you pick up your hand and you sort of have the part that's sorted and the part that's not sorted. And you pick up the next card from the unsorted part and you go, where does it fit in my sorted thing? That's exactly what's happening here. We're picking up the next card, whatever it is. In this case, it's card 15. And we're saying, where is it going to go? Well, it doesn't fit here. We'll move it over. So it fits here. So we'll put it in there. So we pick up the next card. We walk it down until we get to the point where it fits, where it should go, and we put it in. So we have a sorted set of cards over here, and we're walking our way with the new card down to where it's supposed to go. And that walking is the shifting that we're doing here. The aj equals aj minus 1 is it's shifting things over so that we can have a spot to put the card when we find its correct location. Is it okay? Now you know how to play Bridge. No, there's a lot of stuff going on in Bridge. Anyway, how much time does it take? What's the runtime of this code? And also, maybe before we talk about runtime, what should you call this code? You want to call it insertion? Okay, we could call it insertion. Insertion. That's a good name, insertion. I didn't call it insertion, but that's okay. I called it, no, I want you to give me another name. Is there another name? Yeah.
Put in place.
Put in place? That's the same thing that I had. How did you know that? Wow. So clever, so clever. That's what I called it, put in place. It's sort of a, anyway. Not the best name. But anyway, it's the name that I had there. So put in place puts the next card in place, and that's what this subroutine does. This is going to be a subroutine of insertion sort. So it makes sense to call it insertion, but we're going to call it put in place. What's the runtime? No, not people that have already answered. You guys, you can't be freeloaders. You got to participate. That's the whole deal here. What is the runtime of this code? Don't worry. I hardly ever bite. Hardly ever. Theta I. Runtime is theta I. Okay. Anybody else have a suggestion for the runtime? I actually like that. Just asking. Any others? Yeah.
Big O of I.
Big O of I. Excellent. Any other suggestions?
Big Omega.
You really like I. I'm surprised because, the running time, well, maybe I didn't tell you that the size of the array is n. Would you like something else? Yes. It's order n. Oh, good. We've got so many things here. And the sad thing is they're all correct. Wow. How could that possibly be? They're all correct. In fact, I'll even write down one that seems like, whoops. There's also this one. Big omega then. What in the world? How could all of these be correct? Well, because I am not being clear about what I'm asking you. Right? I just said runtime. I didn't say worst case runtime. And yet if I did say worst case runtime, these would all still be correct. But I also didn't tell you something else, which is that is I a parameter, or do I take the max over its value when I'm talking about worst case? So these are all valid worst case running times. They're all correct, but some of them have assumed that I'm doing worst case over the value of I, and some of them have used I as a parameter. And I didn't tell you what to do, so all of these are correct. All of these are valid worst case running times. I have to tell you, it was very good of you to assume that I am not an optimist and that nobody said theta of 1. Because I'm not, I'm a pessimist. So it would be worst case runtime usually that I'd be asking about. But even if you know worst case runtime, in these situations you need to know more about what you want to say. What's the story you want to tell? So this particular story that we want to tell, it depends on what you want to talk about. I mean, we're going to be using this as a subroutine. And so we're going to benefit from analysis that's sensitive to the value of I. We'll benefit from that when we analyze the function that uses this as a subroutine. So I like these, all three of which are true, by the way. I like those because they're more sensitive to the input parameters. But that doesn't mean that these are wrong. So these are sensitive to I, a particular value of I. It's not the worst case over I. These are insensitive to I. They assume a worst case I. Okay. Is anybody confused about this? It really is a way of talking about the function. What is the function that we're trying to talk about when we're applying asymptotic notation? Yeah.
This is only for that, the swap motion, right? So
It's only for this this put in place thing.
for putting it's not for the whole entire line.
No, it's just this function. It's all we're talking about right now. It's all we're talking about. Is it okay? All right. I'm trying to separate two things here. One is the definition of the function that you're trying to talk about, which is the running time. Here it's the worst case running time, maybe sensitive to I, maybe not sensitive to I. That's one thing. And then there's the notion of asymptotics that applies to that function. So once you understand what function you're talking about, then you want to understand something about whether it's less than or equal to some constant times I, greater than or equal to some constant times I, or less than or equal to some constant times n, etc. That's the asymptotics part. The function is the first thing you got to straighten out. And then the asymptotics is kind of like a mathematical condition. It's like, the definition. You have to satisfy that to make things look simpler. Okay? Yeah.
For this case, I is always less than n or inside 0.
Yeah, so this is a good point. So here I'm assuming a couple of things. One is that I is not too big. I is less than the size of A. And the other thing is that I is not too small. I is greater than or equal to 0. And so you're right. I mean, this code doesn't check for those conditions, and you would probably want to do that if you wanted this code to be robust. Okay. Are we good? Any other questions about this? This is a mystery function put in place, and now we're going to use it. It's used in insertion sort. So now, because you know what put in place is like sorting cards. Pick up the next card, put it in place. Pick up the next card, put it in place. Then what insertion sort does is it says, okay, I'll start with I equals 1, and I'll assume there's one card over here, and I'll take another card, and I'll the next card, which is this one, and I'll put it in place. Either it goes before or after this card. And I've got 2 cards. And I pick up the next card. And I put it in whatever order it's supposed to be in, plunk it down. 3 cards. And again, like this. Well, you got it? That's what this for loop is doing. It's picking up a new card each time and putting it in place in the sorted order of cards. Okay, so now, here's the question for you. You are now experts on loop invariants, or at least getting there. I want to know, not loop invariants, I want to know loop invariant. I want to know what is the loop invariant for this piece of code. Insertion sort. Do you need to wake up or talk to other people or something? I'm asking, just if you need something, you like stand up, you want to, we can do that. I always hated that. Actually, it never happens in college, so don't worry. Yeah.
This inverted to be similar to the other one?
Yeah, you're worried, that's all I need.
We're going from the left to right, and we're shifting everything over to the left side, and going forward. I feel like every element for the current iteration is sorted.
Oh, great. Every element up to the current iteration is sorted. That's an excellent loop invariant. Great loop invariant. I just translated what you said into this weird notation because it's easier for me to write. But this is what the loop invariant is. It's simply saying that the first part of the array is sorted, A0 through AI minus 1. This is different than the selection sort invariant. Selection sort had, yes, the first I minus 1, or the first I things were sorted, but it also had that those were the smallest items in the entire array. So not only were they sorted, they were the smallest. Insertion sort doesn't have that. It doesn't use that. It only needs that the first ones are sorted. And then it picks up the next one and it marches its way down through the ones that are already there to figure out where it's going. Does it make sense? Okay. So how hard is it to prove this invariant? It's so easy that I put it on the slides. So there's your invariant. The base case is when you're at iteration I equals 1, because that's the first. I'm using I here to be a proxy for this I. So if you were using a variable that was counting the number of loop iterations, your variable would be something other than I. It would be something like you'd invent a variable like k and say k is the number of times I go through the loop, and that starts off as being 0. But I don't want to invent another variable. I just want to use one that's already there. And I've got a perfectly good one, which is I. But it starts at iteration 1. So I want the loop invariant to hold in the base case before the start of iteration 1, I equals 1. And so, okay, is it true that A00 has only one element? Yes, it is. So it's always in sorted order. So this is great. So we're done. Everybody happy? Is that too quick? Off we go. Okay, induction hypothesis. At the start, this is just basically saying the loop invariant. At the start of iteration I of the loop, A0 through I minus 1 is in sorted order. Right? That's really all that the inductive hypothesis is the statement that you're trying to prove applied to the particular iteration that you're looking at. And then you want to use the inductive step to take you one step farther. And the inductive step is using the inductive hypothesis, show that the loop invariant holds at the next iteration. So in this case, when we make the call to put in place, we know that the first I elements are in sorted order. We're picking up the I plus first, which is cleverly called index I, because C indexes from 0. And we're saying, put it in the right place. And by the proof that we did for, well, did we do that? Did we prove that put in place works? No. Back we go. We have to prove this is true. No, we don't. Do you believe it's true? If you believe it's true, what's the loop invariant? It's a little tricky, the loop invariant, yes? It's a little tricky, because the state of the system that you're at after a certain number of iterations, it's not even an array that contains the original elements. It has a duplicate. Like here, we have a duplicate of 30. So we have to have something that basically says everything after this index is big relative to value, and everything before is still in sorted order. Something like that. Then we can use that to do this inductive step thing. I didn't do it on this slide because it's Friday. And Friday is, you don't have to do this inductive proof day. So I will do this inductive proof and I'll put something up on the website. But it's a little tricky. The loop invariant is just a little tricky and a little messy. But it's not bad, it's just that. Okay, so we're back to trying to use the correctness of put in place, which we've just assumed is true, is working perfectly fine. We're back to using that in order to show that we can go from the inductive hypothesis that A0 through I minus 1 is sorted to the next loop invariant, the next iteration of the loop invariant, which is that A0 through I is in sorted order. And that is handled by put in place. That's exactly what it does. It takes in an array, and it assumes that A0 through I minus 1 is sorted, and it puts I, location, the entity in location I, the element in location I, it puts it into the correct position. It takes the ith card, puts it into the correct position. Okay? You good? So now we've got the invariant again, and it holds for I plus 1 at the start of the next loop. And we're good. Everybody happy? So somebody wrote this code, right? Somebody invented insertion sort. They had to think about what is the property that needs to be true for me to be able to perform these operations and guarantee that the result is sorted. So when they were thinking about this, they were thinking about what is true at every step. And that's what this invariant is capturing. Okay, and then at the end of the loop terminates. It comes out with I being the length of the array n. And by the fact that the invariant is true, not only true at the beginning of the nth iteration of the loop, but that means when it comes out, it's also true at the end of that, because it's just stopping. Then we get that the entire array, A0 through A length minus 1, is in sorted order. And we're good. Okay, that's the little extra bit that you need in order to show correctness, given that you've shown a loop invariant. The little show sorts down at the bottom is a reminder to me to remember to do something. Don't worry, I won't forget. But before I remember that, let me ask you, what's the difference between selection sort and insertion sort? Well, let's just think, what about runtime? What's the runtime of insertion sort? And again, I'm talking about worst case runtime. What's the runtime? much time does put in place take? Order n, big O of n, if you want to be worst case over I, but in fact this is exactly where you can see why I wanted it parameterized by I. Because I know that when I hand it different values of I, it's actually going to be doing no more than I work. So when I is really small, like I is 1, it's blazingly fast to put in place. Just does one comparison and it's done. So that's why I wanted it sensitive to I. It's because I can now write in here that this running time of put in place is big O of I. And if I can do that, then I basically get something where the runtime is big O, well, let's just say it looks, anyway. Big O of the sum from the values of I that I look at, which is 1 to n minus 1 of I. And we know what that summation is because we've all done the homework, because it's already almost due. And that is going to be something like n times n minus 1 over 2, which is big O of n squared. So it's the same thing, the same running time as we had for selection sort. So what's the difference? The runtime's not the difference. What's the difference? Why do we have two sorts, insertion sort and selection sort? Why would people like them? Yeah.
Insertion sort does more operations.
Insertion sort does more operations.
Changing than we have before.
So
for
it's
every iteration.
your conjecture is that it's slower because it's actually doing more work during the process. Okay, that's interesting. Anybody else have an opinion? Yeah.
I have a question. So when you're coming with the runtime, could you also explain that because you're using floating inside a function that already has order of n runtime, can you say that worst case scenario would be n squared because doing n operations against something that already takes n steps to perform?
I could certainly have said, that inner loop, that inner execution, the put in place, takes big O of n time. I could certainly say that. And I can certainly say, therefore, that this loop, which executes n times, is going to execute something that takes no more than some constant times n, and therefore the running time is big O of n squared, the whole thing. I still like doing it in I, and you know why? Because I wanted to remind you about the arithmetic sum here, and the fact that you can do it. That's why I do it, and for no other reason. Yeah.
Yeah. Probably they may look like asymptotically like the same, but actually, for n with like a small value, this insertion sort is more optimal than the.
For small values of n, this insertion sort is faster. That's your conjecture.
Yeah.
Okay. Small values of n is faster. You think it's slower. This is good. We've got an argument going on here. I'm glad you're sitting far apart. Yeah.
I have a question. So what would happen if put in place took like I squared time? Would you just now change the summation to?
Yep.
Okay.
Isn't that cool? If you want to do nested loops, it's nested summations. Yeah.
When we're talking about runtime, so we have worst case, but if we're thinking about average case, could you have like a different average case for every type of input?
Oh, could you have a different type of, could you have a different performance according to average case than the worst case? We have worst case performance, which is the same. When would it be really a good idea to use insertion sort versus selection sort? When would it be a good idea to use selection sort instead of insertion sort? When you think of a situation, let me ask you the first question. Insertion sort. When would be a good time to use insertion sort? When is insertion sort really fast? Remember, I'll run insertion sort while you're thinking. Pick up the next card. Am I smaller? Am I smaller? Am I smaller? Yes. Pick up the next card. Am I larger? Am I larger? Am I larger? No. Smaller, 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 smaller? Yeah. Smaller, smaller, smaller. When? Okay, that's insertion sort, right? Insertion sort does that. Selection sort does something else, but when is insertion sort fast? Boop. Boop. When is it fast? when it's already sorted. I got an array that's already sorted, and it's immediate. It picks up the next element, and it compares it, and it says, oh, I'm bigger. I don't have to go any farther. So put in place takes constant time if you give it an array that's sorted. Of course, who in the world would sort an array that's already sorted? How foolish that is. No. This is actually the usual case. Most of the time, things that have to be sorted are things that are lists of stuff. And those lists of stuff don't just come to you all at once. Like, think about the list of friends on your phone. Like, you're getting new friends all the time now, and you're adding them to your phone, and at night your phone, while you're sleeping, is working away, organizing your list of friends, sorting it in order. But it's starting with a sorted list of your old friends, and it only has to add a few more, maybe 20, maybe 18, whatever, that you met today, and put them back into your list of friends. And that's really fast for insertion sort. It's a very fast update to sorted orders. So we would expect to see that insertion sort just really, really is fast on things that are sorted. And remember, things that are partially sorted, things that are mostly sorted. So that's why this says show sorts. There, we're going to show some sorts. Okay. This is a bunch of sorts across. There's insertion sort in the first column, then selection sort, then bubble sort, then shell sort, then merge sort, then heap sort, then quick sort, and then quick sort 3. We are going to talk in this class about all of those except for 3. 3 of them we are not going to talk about. But not all at once. The ones that I'm interested in right now are these 2. These are the ones that you know about. And so this is this cool website. It's called toptall.com, developer/sorting algorithms. And you can execute these algorithms on different types of inputs. Random inputs, nearly sorted, reversed, few uniques. So there's not very many different values. So let's do it. Wow. So that's very interesting to me, actually. It looked as though, to me, I don't know if it looked that way to you, it looked as though, to me, the insertion sort finished everything before selection sort finished anything. Does it seem right? Let's do it again. Whoops. We knew this was going to happen. The nearly sorted one was fine. But the random one finishes really early. And even in the reversed case, which is kind of weird, I don't expect that. In the reversed case, insertion sort is beating selection sort. So, this is evidence that maybe your assumption is not correct. The number of operations that are happening here, maybe the swaps and the memory accesses are actually in insertion sort's favor as opposed to selection sort. I would guess that this would even get more and more the case if the array got even longer, because selection sort has to go all the way through the array on every iteration. And if you're thinking about memory management, if you're thinking about bringing stuff in from main memory, that's going to touch a lot of fresh memory that has to be brought in, and then it's got to be dumped out, and there's got a movement of memory there. And insertion sort just sort of works a little bit at a time. So that's not what's happening here, though. I don't know why in these small examples it's so different, but it seems to be the case that insertion sort is better than selection sort for many different. Why is insertion sort better for random? This is sort of your average case question. What they've done is they've reordered the input so that the permutation is a randomly chosen permutation of the input size. Why would it be better for insertion sort? I don't have time to think. Oh, let me tell you. The reason is because when you pick up the next card, here I am, I got to pick up the next card. What's the place where this next card is going to be? What's the expected number of comparisons that I would presume to do? About half of the, right? There's probably someplace in the middle of these ones that I've already sorted. So every time I pick up the card, I don't have to go all the way to the beginning, I only have to go halfway. So that means that it's basically half the time of selection sort. Okay. Is it good? This is a cool website. We'll come back to it again, I'm sure. Where was I? Here I am. Okay. Great. Memory. Oh, we're done talking about sorting for the moment and loop invariance, and we're moving on to memory. And the reason we're moving on to memory is because you have a programming assignment which is all about linked lists, and not just simple old standard linked lists. These are doubly linked lists, and not just simple old doubly linked lists. These are quadruply linked lists, not only horizontal but vertically connected into a grid. It's so totally cool, you'll love it. It's great. So anyway, that's what you have to look forward to. But in order to understand all of this stuff, we have to understand memory. How many people are taking 213? This might be a bit redundant for you. But anyway, this is the way your computer works. There's some central processing unit sitting there, and occasionally it needs to do something. And in order to do something, it needs data to work on. So what it does is it yells out to the memory bus. It says, hey, give me something from your memory. And the memory bus says, where? And it tells an address. And it's like memory is a big array. And the address is the index into that big array. And then the memory unit fetches the contents of the array, that is the memory, at that location, 0x0 blah, 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 7, which in this case is 42, and sends it back along the data bus. And then the CPU gets it, and it does whatever it needs to do with it. That's a read from memory. By the way, those numbers over there with the x's, and that's hexadecimal notation. It's base 16. So if you write something in base 16, you can't just use 0 through 9 because that's only 10 digits. So you need extra digits. So you just use A, B, C, D, E, and F. Okay. That's the read from memory. This is the write to memory. Write, the CPU says, I got to write some stuff, I got to store it away, got to send it back out to the memory. I will send it out by telling the memory, here's the address, then here's the data, and I want you to put the data into that address. So what it does is it writes over the location in 0x07 with whatever that data is. It's so simple. It's just a big array, except it's more complicated than that because it's organized. The memory is organized into regions. There's the memory that's used for handling function calls and program, like the parameters that are passed to your program and all that. And if you write a recursive program, it's used to track the recursion. That's the stack. There's a stack in there. That's the stack memory. And then there's the memory that you use when you allocate things using the operation new. When you're going along in C++ and you say, I want a new something or other, that new call allocates memory in a different part of memory. But anyway, they're all arrays. It's just that they are different parts. And then there's, and one of the reasons they do that, one of the reasons they have those, I can't keep talking about this. Yes, I can. I'll tell you one more thing. Do you ever wonder why when your code crashes it says segmentation fault core dumped? Has this ever happened to you? No? How many people have never had a segmentation fault? Really?
It might have happened, never read the message.
Oh, you never read the message? Not bothered? You don't care? Oh, well, it just died. I don't know why, but can't be bothered to read. Read error messages. But no, segmentation fault core dumps means you've asked to access a memory location that's out of your segment. You are allowed certain addresses and other ones are not allowed for you. And you've calculated an address that's out of memory for you, and therefore it says segmentation fault, and it dumps your core. Okay, next time we will talk about pointer manipulation.